What would really happen to our planet in the first 7 days after the nuclear powers push the button? Imagine it, not through a movie, but in stark reality. The first second, a light brighter than 10,000 suns sears the retinas of anyone unfortunate enough to look at it. Almost instantly, a giant fireball, millions of degrees Celsius, erupts, vaporizing everything within a radius of kilometers, concrete, steel, and life itself. Next comes the shock wave, an invisible wall of air moving faster than the speed of sound, flattening buildings like houses of cards, crushing everything in its path. But hell has only just begun. As the shock wave passes, the sudden pressure difference sucks air back towards the epicenter, creating winds with the force of a super hurricane, carrying lethal debris. And then the firestorms are born. Hundreds, thousands of individual fires merge into one colossal sea of flames, engulfing cities, incinerating everything that remains, and sucking the oxygen from the air, causing even those in shelters to suffocate. While the ground is burning, an even more terrifying enemy is forming high above. These firestorms act like giant chimneys, pumping millions of tons of soot, dust, and debris into the stratosphere, far above the weather clouds. Here, there is no rain to wash them away. This black shroud begins to spread, covering the planet like a funeral blanket. This is the dawn of nuclear winter. Sunlight, the source of life on Earth, is blocked. In just a few days, the global average temperature will plummet, potentially dropping below freezing, even at the equator in summer. The daytime sky will become nothing more than a perpetual, gloomy gray. And then the deadly rain begins to fall. Not water, but radioactive fallout, irradiated particles from the explosions carried by the wind for thousands of kilometers. It is invisible, odorless, tasteless, but it is a silent killer. It settles on the soil, in the water, on the plants, turning everything into a source of poison. Anyone exposed to it faces a painful death from radiation sickness. But even before the fallout has a chance to spread, another attack has already brought down civilization. High-altitude detonations would create an electromagnetic pulse, or EMP. In a fraction of a second, it would overload and destroy all unprotected electronic devices. The global power grid collapses. Lights go out, factories stop, water systems fail. The internet, phones, radio, television all fall silent. Humanity is suddenly thrown back to the Stone Age, but a toxic one. By the 7th day, the world as we know it no longer exists. There is no government, as centers of power have been obliterated. There is no law, as enforcement forces have disintegrated. There is no communication to know what is happening beyond your own neighborhood. Supermarkets, if they still stand, would be looted in the first hours. Clean water becomes a luxury. Medicine runs out. Fear and desperation turn neighbors into enemies. The social fabric, built over thousands of years, has disintegrated into dust in just 1 week. Survival is no longer a right, but a brutal, daily battle against hunger, disease, radiation, and your own fellow human beings. This is not a world in recovery. This is a planet that is dying, and the first 7 days are merely the prelude to a death sentence that will last for centuries. Why is surviving the initial blasts just the beginning of an endless nightmare? The answer lies in a concept more chilling than the firestorms themselves: nuclear winter. This isn't an ordinary winter. This is a long-term death sentence for an entire planet. Let's delve into its scientific mechanism. When thousands of nuclear warheads detonate across cities and industrial zones, they don't just flatten everything. The immense heat from the explosions creates colossal firestorms, incinerating millions of tons of material. The smoke, dust, and most importantly, the soot from these fires are blasted into the stratosphere far above the clouds we typically see. At that altitude, there is no rain to wash them away. This layer of soot rapidly spreads, merging into a colossal shroud, enveloping the entire globe. This black curtain would block out sunlight. Scientists estimate that within just a few weeks, the amount of light reaching the Earth's surface could decrease by more than 90%. The daytime sky would become as dark as a dim, moonlit night. The immediate consequence is a catastrophic drop in global temperatures. Average temperatures over continents could plummet by 20 to 30 degrees Celsius, plunging the planet into an artificial ice age. Rivers and lakes would freeze over, summer would disappear, and this leads us to the second and perhaps most terrifying consequence: the collapse of the global food chain. The foundation of nearly all life on Earth is photosynthesis. Without sunlight, plants cannot photosynthesize. All crops worldwide would die in the darkness and cold. Forests would become barren. Grasslands would turn into frigid wastelands. This disaster cascades through the chain. Herbivores would starve en masse. Carnivores would follow. In the oceans, phytoplankton, the very start of the marine food chain, would also perish from the lack of light. The seas would become watery graveyards. For the survivors of the blasts, famine would be an inescapable enemy. Food reserves, no matter how large, are finite. When they run out, there will be nothing to replace them. Agriculture, humanity's 10,000-year-old civilization, would be wiped out in a single season. But the nightmare doesn't stop there. Alongside the darkness and the cold, there is a silent, invisible killer: long-term radiation. Nuclear explosions release vast quantities of radioactive isotopes into the atmosphere. Stratospheric winds would carry these deadly particles across the planet, creating what is known as global fallout. It would descend upon the land like an invisible rain, contaminating everything: the soil, the water sources, the air. Substances like cesium-137 and strontium-90 would accumulate in living organisms, causing cancer, immune system failure, and other horrific diseases. But its most terrifying impact is on the genetic code. Ionizing radiation shatters DNA molecules, causing genetic mutations. Children born after the catastrophe, if any, could suffer from horrific birth defects. The entire ecosystem would be damaged at a genetic level. Animals and plants would mutate or become sterile. The planet's biodiversity would be dealt an unrecoverable blow. So, what is the full picture of a post-nuclear Earth? It is a world shrouded in darkness, freezing to the extreme, and poisoned by an invisible enemy. A planet where the sun is but a distant memory, where food is non-existent, and where the air you breathe and the water you drink could be slowly killing you. This is no longer a home. It is a planetary tomb. Surviving the first few days isn't a victory. It's merely purchasing a front-row seat to witness the slow, agonizing death of everything you've ever known and loved. The Earth would be unable to support complex life for generations, perhaps even centuries. That is why the answer doesn't lie in hiding underground. The only answer is to leave. Mars has always been considered Planet B, so why is it a terrible choice in this apocalyptic scenario? In our culture, Mars is more than just a planet. It's a symbol, a dream of a new beginning.
From the pages of science fiction to the bold plans of tech billionaires, the red planet has always been the ultimate destination, proof that humanity can reach beyond its cradle, Earth.
But in the grim reality of a post-apocalyptic evacuation, that beautiful dream quickly turns into a deadly trap. And the reason lies not with Mars, but with the one thing we don't have: time. First, let's talk about distance. This isn't just a number in an astronomy textbook. It's a chasm separating life from death. A trip to the moon, our next-door neighbor, takes about 3 days. 3 days in a cramped, dangerous space. But it's a manageable journey. A trip to Mars? We're talking about 6 to 9 months, depending on planetary alignment. 9 months. Try to imagine that. 9 months drifting in the infinite void, in a spacecraft like a bullet fired with no possibility of turning back. Every passing day is a day you face the risks of cosmic radiation, technical malfunctions, and psychological breakdown. Your ship isn't a luxury liner, it's a fragile lifeboat in a stormy cosmic ocean. And during those 9 months, Earth, the only home you've ever known, is dying behind you. Every signal received, if any, will only be fading echoes from a world that has perished. This is not an expedition. It is a suspended death sentence. Second, and perhaps even more critical, is the issue of communication delay. On Earth, we are accustomed to instant video calls, to sending and receiving information in the blink of an eye, but physics is unforgiving. The vast distance between Earth and Mars creates an unavoidable signal delay, averaging about 20 minutes one way. That's a total of 40 minutes for a question and an answer. Imagine this: your life support system flashes a red alert. You send an urgent message to Mission Control, wherever it may still exist on Earth or has been moved to the Moon. You wait. 20 minutes pass in deafening radio silence. Finally, your signal reaches its destination. Engineers on the ground frantically analyze the problem. They find a solution and send it back to you. Another 20 minutes pass. By the time you receive the instructions, 40 minutes have elapsed since the incident began. In many cases, 40 minutes is more than enough for disaster to strike. Controlling rovers on the surface, providing remote medical assistance, or simply getting advice in an emergency situation all become impossible. You are having a conversation with a ghost from the past. You are utterly alone. Third, there is the challenge of landing. Safely landing on Mars is what NASA calls the 7 minutes of terror, and that's with the support of the greatest minds on the planet and a global communications network. The Martian atmosphere is a tantalizing paradox. It's thick enough to create friction and scorching heat as your spacecraft plummets at tens of thousands of kilometers per hour, yet too thin to effectively use parachutes as you would on Earth. You must rely on a sequence of extremely complex and millisecond-precise maneuvers, from the heat shield to a supersonic parachute to retro-rockets. The slightest error, and the ship carrying humanity's last hope will become a new crater on the red planet's surface. In a post-apocalyptic scenario, there will be no mission control in Houston to monitor and assist you. You are performing the most dangerous blind jump in history, with the lives of everyone on board as the stake. Finally, even if you overcome all those obstacles and set foot on Mars, the nightmare has only just begun. That is the uncertainty of resources. We know there is water ice on Mars, but where is it, how deep is it, and is it easily extractable with the limited technology you brought with you? The atmosphere is mostly carbon dioxide, which can theoretically produce oxygen. But the MOXIE instrument on the Perseverance rover was just a small-scale experiment. Establishing a self-sufficient base on Mars isn't as simple as pitching a tent.
It requires building an entire complex chemical industrial plant to create air to breathe, water to drink, and fuel for future trips, all from scratch on a foreign and harsh planet far from any help.
Mars is not a turnkey home. It is a massive and risky construction project. In a race against death, betting the survival of the entire species on such an uncertain project is an act of suicide.
The dream of Mars is beautiful, but it's for a humanity at its peak, not one on the brink of extinction. How can a barren ball of rock right next to us become our only hope?
The answer lies not in what the moon has, but where it is. In a desperate race to escape a dying planet, distance is the most brutal enemy. And in the fight against that enemy, the moon is our only ally. The decisive advantage, the single factor that outweighs all other variables combined, is proximity. 3 days, that's all that separates us from a potential sanctuary. A 3-day journey compared to a grueling, perilous 6 to 9 months to reach Mars. Imagine this. While the first ship to Mars hasn't even completed half its journey, we could have already made dozens, even hundreds of supply runs, transporting essential personnel and equipment to the moon. This isn't a leisurely scientific expedition. This is an emergency evacuation. Every hour, every minute is measured in lives. We simply don't have time for year-long journeys. This proximity also unlocks another strategic door, near instantaneous communication. The signal delay between Earth and the Moon is only about 2.6 seconds for a round trip. What does this mean in practice? It means the best experts remaining on Earth can operate construction robots on the lunar surface in real time. A surgeon in an underground bunker could guide a medical robot through a complex procedure on a settler. Engineers could debug and repair critical systems remotely with absolute precision. Conversely, with a communication delay of up to 40 minutes to Mars, every operation must be either fully automated or performed by those on site with extremely limited support. Any unexpected problem could become an unrecoverable disaster. The moon allows us to extend our hands and our minds into space, while Mars forces us to sever that connection. But proximity is just the ticket to entry. To truly survive and thrive, we need resources. And this is where the moon reveals its greatest secret, a treasure hidden in the coldest, darkest places. That treasure is water ice. For billions of years, the craters at the moon's poles have never seen a single ray of sunlight. In these prominently shadowed regions, temperatures can plummet below -200 degrees Celsius, turning them into perfect cold traps. Comets and asteroids, icy messengers from the outer solar system, have continuously bombarded the moon, and any water molecules that landed in these craters were trapped forever. Recent space missions like NASA's Elsie-Cross and India's Chandrayaan-1 have confirmed the existence of hundreds of millions, perhaps even billions of tons of water ice. This isn't just a scientific discovery, it's our key to survival. This water ice, when mined and melted, will provide drinking water for the settlements. But more importantly, through a process called electrolysis, we can split water into its constituent components, oxygen and hydrogen. Oxygen to fill our habitats, for us to breathe. Hydrogen, a critical component of rocket fuel. Suddenly, the moon is no longer a final destination. It becomes a massive refueling station in space. We can produce fuel right on site, instead of having to costly and dangerously launch it out of Earth's immense gravity well.
This dramatically reduces the cost and complexity of all space operations, paving the way for a self-sufficient economy and even for missions farther afield in the future when humanity is ready. But the Moon's resources don't stop at water. Its surface is covered in a fine dust called regolith, and within this dust is an element extremely rare on Earth but abundant on the Moon, helium-3. For billions of years, the solar wind, a stream of charged particles from the Sun, has continuously blasted the Moon's unprotected surface and deposited vast quantities of helium-3. Why is this important? Helium-3 is considered the ideal fuel for second-generation fusion power. A fusion reaction using helium-3 does not produce high-energy neutrons, meaning it is safer, cleaner, and does not create long-lasting radioactive waste like current fission reactors. Mining helium-3 on the Moon could provide clean, nearly limitless energy not only for the colony, but could also be shipped back to Earth in the future, becoming the engine for the planet's rebirth. The Moon, once a refuge, could become the source of energy salvation for the very home we left behind. Finally, the Moon offers a strategic advantage that cannot be measured in tons or kilograms. It is its position as the ultimate high ground. From the lunar surface, Earth is not a faint blue dot. It is a massive sphere, hanging in the black sky, allowing us to observe it with unimaginable detail. We can track the spread of radioactive fallout, the changes in weather patterns during the nuclear winter, and eventually, the first signs of life's recovery. The Moon will be our laboratory, our observatory, and our library. From there, we can study our home planet, understand our mistakes, and plan for a distant return. It is a beacon of hope, a constant reminder of what we lost and what we must strive to rebuild. It allows us to keep one foot in the past while stepping with the other into the future. It's not just about running away. It's about safeguarding humanity's legacy from a position of safety, waiting for the moment to reseed life on the barren soil of Earth. Who gets to go, and who gets left behind? This isn't just a logistical problem. It is the single greatest moral dilemma humanity has ever faced. A final, planet-wide triage. Welcome to the selection for the cosmic Noah's Ark. The process of deciding who carries humanity's torch to a new world is a brutal one, shaped by cold calculus and questions with no easy answers. First, and most obviously, are the skill-based criteria. A nascent lunar society has no need for hedge fund managers or social media influencers. It needs builders, fixers, and creators. Mechanical, electrical, and software engineers, surgeons, general practitioners, and geneticists. Geologists to find resources, agronomists to grow food in artificial environments, and physicists to operate the compact nuclear reactors that tower everything. The list is a grim indictment of what our society once valued versus what is actually essential for survival. Next is health, both physical and mental. Every candidate would undergo the most rigorous medical screenings ever devised. No chronic illnesses, no latent genetic markers that could endanger themselves or future generations. But perhaps more important is psychological fortitude. Can you handle utter, absolute isolation? The crushing guilt of being one of the few survivors? Can you look up into the sky and see Earth, your former home, as a dead gray orb without breaking? These psychological tests would be brutal, designed to shatter even the strongest, because only the unbreakable can go. And then there's the cold biological factor, genetic diversity. To re-establish the human species without the risk of a debilitating genetic bottleneck, the pioneer group must represent the widest possible cross-section of the human genome. This means the selection would have to transcend old national, racial, and ethnic boundaries. A healthy shepherd from the Andes might be more genetically valuable than a Nobel laureate scientist from a homogeneous lineage. So who makes these life or death decisions? Several models have been proposed, each of them terrifyingly flawed. Would it be a global council, a remnant of the United Nations, attempting to allocate spots fairly among nations? A scenario certain to become mired in the same politics, nationalism, and favoritism that caused the catastrophe in the first place. Or does the power lie with the private corporations that built the escape vessels? A cold plutocracy, where a seat to the moon is sold to the highest bidder or awarded to the most loyal employees. The future of humanity decided by those who could afford to buy it. Perhaps the fairest way would be a global lottery system. Every surviving person, everywhere, gets an equal chance. A teacher, a plumber, a farmer, anyone could be chosen. This sounds democratic, but it could be a practical death sentence. A ship full of randomly selected people might lack the critical skills needed to operate it, let alone build a civilization. The ethical dilemmas cut even deeper. Do we prioritize world leaders, those with experience in governance? Or are they the very people responsible for this destruction? Do we save seats for artists, poets, and musicians? Is humanity worth saving if we only salvage the mechanics of survival but lose its soul? The most agonizing question of all, do we take children? Every child takes a seat a skilled specialist could fill. But a society without children is a society with no future. Ultimately, inevitably, this selection process would ignite chaos and conflict. Once the list of the chosen is announced, what happens to the billions left behind? Desperation would curdle into rage. Launch sites would become fortresses, besieged by those trying to fight their way off a dying world. The chosen would not board their ships as heroes, but as refugees, haunted by the screams of those they had to leave behind. The selection is not just about deciding who lives, it's about deciding which version of humanity gets a second chance. And that is a choice that will define and perhaps haunt us for the rest of time. How do you turn moon dust and ice into a habitable city? This question is more than just an engineering challenge, it's a question of our very survival. When the first survivors set foot on the lunar surface, they don't bring with them the materials to build a city. They bring only knowledge, technology, and an iron will to turn desolation into a home. The answer lies in a core principle: living off the land, or more accurately, living off the celestial body. The first and most critical step is building shelter. Not temporary inflatable tents, but permanent structures capable of shielding against the moon's greatest enemy, cosmic radiation. Without a protective atmosphere and magnetic field, the lunar surface is constantly bombarded by high-energy particles from the sun and deep space. An unprotected human would receive a lethal dose of radiation in just a few hours. So, what do we use to build walls several meters thick? The answer is right under their feet: regolith. Regolith is the layer of dust, soil, and broken rock that covers the entire lunar surface, created over billions of years by micrometeoroid impacts. It's not like sand on Earth. Its particles are extremely sharp, like tiny shards of broken glass, and highly abrasive. But this dangerous material is the key. The technology of choice is large-scale 3D printing. Imagine an army of autonomous robots, equipped with giant 3D printers.
They would move across the surface, scooping up the regolith and using one of two primary methods. The first method is laser or microwave sintering. A focused beam of energy would melt the regolith particles in place, causing them to fuse together into a solid layer. Layer by layer, the robots would build up the walls, domes, and entire structures of the settlement. A second method might involve using a polymer binder transported from Earth mixed with regolith to create a kind of lunar concrete. Either way, the result is a habitat built from local materials, with thick walls that can block nearly all harmful radiation. Space architects wouldn't build skyscrapers. Instead, they would favor dome-shaped or semi-spherical structures, as this is the most efficient shape to withstand the air pressure from within. Much of the settlement would likely be built partially or fully underground to take advantage of the natural regolith as an additional shielding layer. An even more attractive option would be to find ancient lava tubes, giant caverns beneath the surface created when the Moon was still geologically active. Building a base inside these tubes would offer near absolute protection from radiation and micrometeoroid impacts, while also maintaining a much more stable temperature than the surface. Once a safe roof is overhead, the next challenge is creating a breathable atmosphere and water to drink. This is where the closed-loop environmental control and life support system, or ECLS, comes into play. The ECLSS is the artificial heart and lungs of the entire colony. It must work perfectly, recycling 100% of everything, because there is no room for waste. Water is the most precious commodity. The initial supply will come from mining the water ice in the permanently shadowed craters near the poles. Mining robots will excavate this ice, melt it, and purify it. But this supply is finite. Therefore, once inside the settlement, every single drop of water must be recycled. Urine, water from breath and sweat, wastewater from washing and cooking, all of it will be sent through a complex, multi-stage filtration system, using physical filters, chemical reactors, and distillation to produce pure water, cleaner than the best tap water on Earth. This isn't science fiction. This technology has been used on the International Space Station for years, but on the Moon, it would have to be scaled up to the size of a city. The same goes for air. Humans inhale oxygen and exhale carbon dioxide. In a sealed space, CO2 would quickly build up to lethal levels. The ECLS will constantly draw in the air, using chemical filters to scrub out the CO2. This CO2 is not discarded. Instead, it's fed into a reactor called a sabatier, where it's combined with hydrogen, split from water through electrolysis to create methane and water. That's right, the process creates water, which is then fed back into the system. The oxygen needed for breathing is generated by electrolyzing water, splitting it into hydrogen and oxygen. It's a nearly perfect loop. Solid waste, including human waste and organic trash, would also be processed. It could be incinerated to generate energy, or biodegraded in reactors to be turned into fertilizer for plants. The golden rule is, on the Moon, there is no such thing as trash. A city like this needs a massive and stable source of power. The Moon has a huge advantage. No clouds, no atmosphere to obstruct it, the sunlight is incredibly powerful. But it also has a fatal flaw. A lunar night lasts for the equivalent of 14 Earth days. For 2 weeks, the surface temperature plummets to below -170 degrees Celsius and darkness reigns. Relying solely on solar power would be suicide. Therefore, the energy solution must be a dual system. During the lunar day, vast solar farms with high-efficiency panels would be deployed on the surface. They would power the entire settlement's operations and simultaneously charge energy storage systems, which could be advanced lithium-ion batteries or hydrogen fuel cells. But when the 2-week twilight begins, another power source must take over. That source is nuclear power. Not the giant, complex nuclear power plants of Earth. Instead, these are small, compact, safe, and reliable fission reactors, like NASA's Kilopower project. Each of these reactors is only about the size of a trash can, but can generate 10 kilowatts of electricity continuously for over a decade without refueling. A network of dozens or hundreds of these reactors would form the energy backbone of the colony, ensuring that life support, heating, and critical operations are never interrupted, even in the longest, coldest night. The combination of abundant solar power by day and steady nuclear power by night creates a resilient and robust power grid, strong enough not just to sustain life, but to fuel growth. Finally, surviving is not enough. Humans need to eat. Continuously shipping food from a dead Earth is impossible. Food security must be established on site. This will take place in underground gardens or inside heavily shielded domes. There will be no traditional fields of soil. Instead, there will be advanced hydroponic and aeroponic systems. In hydroponics, plant roots are submerged in a nutrient-rich water solution. In aeroponics, the roots hang in the air and are periodically sprayed with a nutrient mist. Both methods use over 90% less water than traditional agriculture and allow for complete control over the plant's growing environment. Natural sunlight will be replaced by arrays of optimized LED lights emitting the precise wavelengths of light that plants need for the most efficient photosynthesis. Crops will be carefully selected. Fast-growing leafy greens like lettuce, energy-rich tubers like potatoes and sweet potatoes, and protein-rich legumes like soybeans. These vertical farms with stacks of growing trays will maximize production space. They not only provide food, but also play a vital role in the ECLS, helping to convert CO2 into oxygen and providing a precious patch of green for the settler's psychology, a reminder of the home they left behind. Thus, from dust, ice, and technology, a city begins to form. 3D printed walls rise from the regolith, inside which air and water are endlessly recycled, powered by a marriage of the sun and the atom and sustained by artificial gardens. It is a complex symphony of engineering, biology, and chemistry, an extraordinary testament to human adaptability. Turning a dead world into an oasis of life is not a miracle. It is the result of ultimate ingenuity and determination. Besides construction, what potential dangers could wipe out the colony at any moment? The answer is terrifying. Almost everything. Erecting walls and domes is merely winning the first battle. The real war, the endless war, is against the moon's environment itself, a silent, ruthless, and tireless enemy. The first and most invisible enemy is empty space. On Earth, we are protected by two invaluable shields, our atmosphere and our magnetic field. They block or deflect a constant storm of cosmic radiation bombarding us from distant stars and our own sun. But the moon has neither. It is a naked body, fully exposed to the wrath of the cosmos. Galactic cosmic rays, or GCRs, are subatomic particles accelerated to near the speed of light by supernova explosions. They slice through metal and living tissue with ease, shredding DNA strands, causing cancer, and damaging the central nervous system. Then there are solar particle events, or solar storms. When the sun erupts, it spews streams of high-energy particles that could kill an unshielded astronaut in a matter of hours. Living on the lunar surface is like standing in a perpetual nuclear firing range. The only solution, and the most drastic one, is to go underground.
Settlements must be buried under several meters of regolith. This layer of rock and dust, once an obstacle, now becomes a life-saving shield, absorbing the most dangerous particles and creating a relatively safe haven below. The second enemy is more insidious. It's everywhere, it clings to everything, and it can kill you from the inside. It's lunar dust. This isn't the soft, fluffy dust you sweep from under your bed. Lunar dust, or regolith, is the product of billions of years of relentless micrometeorite impacts, with no wind or water to erode its sharp edges. Under a microscope, each particle looks like a shard of broken glass, razor sharp, with jagged edges and spiky shapes. It's also electrostatically charged, causing it to cling bizarrely to every surface. For machinery, it's a nightmare. It grinds down seals, jams joints, obscures solar panels, and damages delicate electronics. A spacesuit covered in this dust could be abraded to the point of leaking after just a few spacewalks. But the greatest danger is when it gets inside the habitat. If inhaled by astronauts, these sharp particles embed themselves in lung tissue, causing a chronic inflammation similar to silicosis, a deadly disease for miners on Earth. It cannot be expelled by the body. Once it's in, it's there forever, slowly destroying your ability to breathe. The fight against dust, therefore, requires advanced technologies, multi-layered air filtration systems, magnetic shields to repel dust from critical areas, and strict decontamination protocols at airlocks, where spacesuits must be meticulously cleaned before anyone is allowed inside. Next is the enemy of extremes, temperature. A lunar day lasts for nearly 29 Earth days. During 2 long weeks with no sunset, the surface is scorched by direct, unfiltered sunlight, with no atmosphere to diffuse it, sending temperatures soaring to 127 degrees Celsius, hot enough to boil water. But when the 2-week-long night falls, with no blanket of air to retain heat, the surface cools down with terrifying speed, plunging to minus 173 degrees Celsius. This temperature swing of over 300 degrees creates a tremendous thermal shock. Metal can expand and contract to the point of fracturing. Electronics can be permanently damaged. Living underground is once again the key solution, as the thick regolith acts as an excellent insulator, keeping the temperature within the habitat far more stable. But even if these physical enemies can be managed, there remains one final enemy, perhaps the most dangerous of all, because it attacks from within. It is the human mind. The isolation is absolute. You are on a barren rock, far from everything and everyone you have ever known. Living quarters are cramped, and every action is monitored for safety. But the most devastating thing is the view from the window. The Apollo astronauts experienced the overview effect, a profound sense of awe and connection upon seeing Earth, a vibrant blue marble floating in the darkness. But the survivors of a nuclear war would experience a reverse overview effect. They would look up and see a gray, sick planet, shrouded in clouds of radioactive dust. It would not be a symbol of hope, but a giant tombstone, a constant reminder of the world that was lost, of the family and friends left behind. The psychological burden of witnessing the death of your home planet every single day is immeasurable. It could lead to deep depression, internal conflict, and the complete mental collapse of an entire community. Therefore, maintaining mental health becomes a top priority, on par with providing air and water. Robust psychological support systems, virtual reality for simulating earthly environments, and a common purpose, a reason to keep going, will be essential tools in this fight.
Radiation, dust, temperature, and despair. These are the four horsemen of the lunar apocalypse. Building a city is just the beginning. Surviving in it requires constant vigilance, technological ingenuity, and an unbreakable strength of spirit. Once survival is assured, how will humans on the moon create a civilization? When the life support systems are stable, when food is secure, and the domes are safe from radiation, the biggest question shifts from how to survive to how will we live? This is no longer a battle with the environment, but the construction of a society from scratch. The first power structure will likely resemble nothing we've known on Earth. The old political systems, whose arguments and divisions contributed to the destruction of their home world, will be seen as obsolete and dangerous. Instead, a technocracy might take hold. In an environment where a single miscalculation could kill everyone, the voice of the chief air filtration engineer will carry more weight than any orator. Decisions will be based on data, efficiency, and cold logic. However, can humans live without ideology, without passion? Another option is a radical direct democracy, enabled by technology. Every citizen, from geologists to hydroponics specialists, could vote on every major policy through their personal terminals. Transparency would be absolute, but would it lead to mob rule or paralyze urgent decision-making? Most likely, Lunan society will be a hybrid of both. A council of experts managing the critical survival systems, while social issues, resource allocation, and future direction are decided by the collective will. But a society is more than just laws. It has a soul. Where will Lunan culture spring from? It will be shaped by the eternal silence outside, by the cloudless black sky, and by the tragic image of the gray-blue earth hanging in space, a constant reminder of a lost paradise. Art might no longer be paintings of sunsets or sunrises, but intricate 3D sculptures printed from regolith itself, or digital symphonies that mimic the breathing of the station. Language will also evolve, creating new words to describe their unique experience. Earthshine for the faint blue light reflected from the mother planet, dome fever for the claustrophobia, or the long night for the 14-day cycle of darkness. New rituals will be born. Not Christmas or Lunar New Year, but a festival of light when the sun finally crests the horizon after the long night. Or Earth Remembrance Day, a day of silence spent gazing at the dead planet. Then the most momentous occasion will arrive. The first cry echoes in the silent environment of the moon. The first child is born off Earth. This is not just a medical event, it is a declaration. This child, a true Lunan, will grow up in 1/6 gravity. Will never feel rain on their skin or breathe fresh air. To them, Earth's blue sky is just a fairy tale. This birth is the final proof that humanity is not just clinging to life, but putting down roots in a new world. It is the bridge between a ruined past and an uncertain future, and that leads to the final, most haunting question. Will this new society repeat the old mistakes? Are the seeds of greed, jealousy, and the lust for power, the very things that destroyed Earth, still hidden in human DNA? As the colony grows, will factions form? Will wars over resources, even just water or energy, erupt once more? Or will the daily sight of the consequences of their folly, a desolate, silent Earth, be the harshest lesson, a permanent antidote to humanity's self-destructive nature? From the ashes of the past, can they build a utopia, or are they simply carrying the seeds of their own destruction to a new world? What is humanity's ultimate purpose on the moon? To escape forever or to one day return?
The answer is not simply one or the other. The lunar colony is not a lifeboat for escape, but an archive, a beacon guarding the heritage of an entire planet. Its first and most sacred role is to be the guardian.
Beneath the regolith, shielded from cosmic radiation, will lie the greatest archive ever created. Not just digitized data of every work of art, every book, every piece of music, but a global gene bank. The seeds of every plant species, the DNA of every creature, and the diverse genome of humanity itself, all cryogenically preserved, waiting for the day they can be sown again on their mother world. But merely preserving memory is not enough.
The second mission, one that will span centuries, is to watch. From the moon, humanity will have a unique vantage point to monitor Earth's recovery. Telescopes will constantly scan the once blue, now gray planet, analyzing the atmosphere, measuring radiation levels, and searching for the first signs of reviving life.
Every small patch of green that reappears, every drop in radiation readings, will be a recorded spark of hope. The long-term plan is not to forget, but to wait with scientific patience, to pinpoint the exact moment when Earth can once again open its arms to its wayward children. During that long wait, humanity will not merely survive, they will thrive. And this is the moon's third role, a launch pad. It is here, on this barren ground, that we will learn how to truly live in space. The harvesting of water ice to create rocket fuel on-site will turn the moon into a way station, a massive spaceport for further journeys. The lessons learned in building closed-loop habitats, in enduring a hostile environment, will be the foundation for reaching Mars, the moons of Jupiter, and beyond. The moon is not the end of the line. It is the starting point for humanity's multi-planetary era. It is living proof that even after the worst imaginable disaster, we can get up and continue to explore. Ultimately, all of this converges into a single message. Existence on the moon is a constant reminder of the fragility of the home we lost and of the extraordinary resilience of life. It is a dual responsibility, to preserve the past and to build the future. The Lunans, the children born under a black, star-dusted sky, will grow up with the story of a brilliant blue planet, and they will carry within them a mission, not just to survive, but to ensure that such a horrifying mistake is never repeated, not on Earth nor on any other world humanity touches. Hope lies not in running away, but in learning, rebuilding, and one day, perhaps, returning.